So, of course, I'd like to say thank you, everyone, for joining. My name is Cody Armstrong, and today we're talking about creating complex assembly motion in Onshape. And a big part of the reason we created this webinar was really just to answer a lot of frequently asked questions we get from users about how to create certain types of motion. As I always say with these webinars, we really encourage you to ask any questions that you'd like. There's a questions dialog, and you go to webinar control panel. Feel free to type in any question, and I'll do my best to stop and address the questions as we're going through today's webinar. So, short webinar for you today. What I thought we'd do is just put together a few common examples of complex motion in your assemblies and how you'd go about creating that in Onshape. So, let's get started. Now, I have a brief agenda for you. We're going to start really basic. So if you're just getting started with Onshape and you're trying to understand, some of the assembly process, I'm going to do a brief introduction to mates and relations. Won't spend a ton of time discussing kind of the basics of mates and relations, but I will discuss it just briefly. If you are interested or if you're just getting started with assemblies, I really encourage you to check out our past webinars. If you go to our YouTube channel, you'll find a playlist of our previous webinars, including webinars that discuss kind of the basics of assemblies. The idea behind today's webinar is trying to discuss some of the more complex motion that you might create using some of these tools. So brief introduction, then I want to get into a few simple examples. And then we're going to start basic with, simple mechanisms, just a few parts to try and understand how to set things up. But then I want to get into what's possible. What can you create and demonstrate using assembly motion in Onshape. Now, as I always say with these webinars, again, feel free to ask any questions that you'd like. There's, again, a questions dialog there, and you go to webinar control panel. Feel free to ask any question, and I'll do my best to stop and address them. Now, I actually have a few questions of my own for you, and I hope you'd bear with me for just a moment here. I'm always curious, in the audience that's with us today, are you using Onshape in a professional environment? Are you using Onshape as maybe a maker or hobbyist creating 3D printed projects? Are you using it for professional use? So if you would, just take a brief moment to fill out the poll, and I'll close it out. All right, I'll close that poll out, and let's go back to our slides here. So thank you, everyone. Let's get into the basics here. And the first thing I want to mention is, of course, kind of the basics of mates and relations. They're the core of our assemblies. So when you're building assemblies in Onshape, mates are the key pieces that hold all these parts together. And so the way to think of it is you're constraining parts relative to each other. And we use something that's a bit different than many traditional CAD systems. And the idea behind it is trying to simplify the process. Instead of using a combination of faces and so on, we use mate connectors to define the relationship between parts. And it just simplifies the process. It often means that you have fewer mates than you would in a more traditional system. Now, the key thing with Onshape is the mate type, the mate that you choose, defines the degrees of freedom. And if you're not familiar with the term, degrees of freedom just mean defines the movement that's allowed. And so if I want to define, a part to another part and I want it to be able to rotate or pivot or, those types of decisions make a difference in what mate I choose. So the key thing, again, when you're building your assemblies, everything is, quote unquote, free floating. Now, you can move everything out freely. I constrain the parts with mates. Now, what is a relation? And this is something that also, of course, ties into with our assembly. And the key thing with relations, and it's very much what we're talking about here today, is those are the tools that you use to actually create the relationship between mates and give you that movement between parts. And I think that's the key thing. So it uses the existing mates, and that's an important thing to point out. So we're taking existing mates that you've already used to bring the assembly together, and we're defining relationships between those mates. And it makes it easy to define, for every rotation of this, I want this to move a certain amount, right? Because it's all driven by those mates. Now, it constrains the degrees of freedom in the actual mates. And I'll get into an example, so forgive me if I'm losing you. Just bear with me for a moment. And there are a few different types of relationships. You'll see them on the far right of the assembly toolbar. We have gear relation, screw relation, rack pinion relation, and a linear relation. So I'm going to get into examples of these in just a bit, so bear with me. But the mates and the relations are important pieces to bringing together and actually getting correct motion out of our assembly. So let's dig into it, and I want to start with gears. And I think that's the most common question I get asked when we talk about the moving relationships between parts is how do I actually recreate gears and get them, animating in Onshape? And it's actually really simple. We have a specific command called a gear relation. And what you do is you define a ratio between your gears, and more specifically between the mates that constrain those gears. And I'll show you this in just a moment. And essentially what we're doing is we're choosing two mate connectors with rotational degrees of freedom. They need to be free to spin, right? And we define a relationship between those two, and we say for every one rotation of this rotates X. So real simple. Let's get into an example of it. And forgive me now, I'm going to be doing a lot of jumping back and forth. You see I have quite a few tabs open here. And I want to start with a simple gear example. And as I mentioned before, I'd like to start basic and then kind of show you what's possible. So this is a real simple example where I have two different gears. And when I rotate one, I want the other to rotate at a certain ratio. Now, the important thing that I want to point out before we get into the gear relation itself is notice that the two revolute mates are what are constraining the gears. So these gears are still free to spin. I can grab them and drag them, and they're free to rotate. And that's important because that's what we're constraining with our gear relation. So real simple. As I mentioned before, you'll find all the relations on the far right of the toolbar. So gear relation, rack pinion, screw relation, and linear. And I select gear relation. I choose the two mates, or the two rotational degrees of freedom that I want to control it, and then define a ratio between them, first to second. So we'll say 1.25. Okay. So 1.25, that means, of course, for every one rotation of this will rotate 1.25. I hit the green check. Now I can grab and drag, and notice I'm getting that correct gear relationship. So that's one of the first and most common examples that I get asked. How do I make gears interact with each other in an on-chip assembly? And if you're not aware of it, you can right-click any mate and animate it if you're interested in actually animating the motion and not just dragging it. So that's a simple example of a gear. Now, one of the questions I often get asked, and it's specific to gears, is how do I get the teeth to mesh properly? And it's a commonly asked question, especially if you're importing gears from other CAD applications or, maybe from some, library that you have of gears. They're not going to automatically come in the exact right position. So a tip that I have is you can edit mate connectors and rotate them. Here I've rotated a mate connector 21 degrees to get the gears to line up properly. Now, if you actually model the gears in a part studio, they'll come in that position. But if you're importing gears like I've done here, you'll need to set that rotation to get the teeth of the gears to mesh properly. So just keep that in mind. It's a tip that I have. You can edit individual mate connectors and rotate or offset or whatever it is that you want to do. Now, question, how do you specify the start position of these types of mates? And again, that's all in the actual mate connector itself. So you can define an individual position. Here I'm defining 21 degrees as my start position. If this were a different example where I wanted, maybe it's a linear travel, I can define an X, Y, and Z start and end position, or even a limit for the amount of travel. But that's all in the mate connector for the mate. So you'll see under each of the mates, we have the mate connectors that comprise it. All right, so let's get into a little bit more complex example. Now, real simple, 3 parts. We have 2 gears and the plate that they're mounted on. And of course, the main thing I want to illustrate there is you need to have that rotation for the gears to work. And that's where the 2 revolute mates come into play. Now, what I want to show next is kind of what's possible with this. And this is a 4-stage planetary gear set. And of course, planetary gear set has a lot more details to figure out, but really the process is the same. And if you look at this example, there's 4 different gear relations that drive the relationship between the sun and the ring, right, in the various gears. And this can be compounded. So this is one subassembly, one stage of that planetary gear set. And if I jump back to the full 4 stages, all of them are tied together with simple fasten mates. So not going to go into a ton of detail about the pieces that put this together, but just keep in mind that it compounds. So if I create a series of gear mates and then I put them into a subassembly and assemble those to more gear mates, then I realize you can have something like this where I actually get 4 times or 4 stages of planetary gear sets that all drive one another. And I think the gear reduction in this is something like 212 to 1, right? So you just realize that, I showed you a simple example, but you can do very complex gear mechanisms using a simple gear relationship and just doing, several. Each one of those stages has 4 different gear relations, and then I just take each stage, bring them together with a simple fasten mate that ties them together, and then when I rotate one, the other rotates, and I get that gear reduction. So that is a gear relation. It's one of the more common examples, or one of the more common questions, I should say, that I get, and one that I always like to point out. And again, you'll find it in the far right of the toolbar here. Now, the next one that I want to point out, jumping back to my slides real quickly, very similar to this, in fact, identical, actually. What about worm gears? So every time I show a simple gear example, the question then comes up, well, what about worm gears? How are those treated? Are those any different? And the answer is no. They're exactly the same. The only difference is, of course, they're in different directions, but in terms of defining the gear relationship, they're identical. All you're doing is defining a ratio between the 2 mates. So let me show you a simple example of this. Bear with me for just a second here. So this is the worm gear assembly, and if we scroll down here, I have a revolute gear, a revolute mate, I should say, that defines the worm, and I have a revolute mate that defines the worm gear. And all I want to do is define for a certain amount of rotation of this, I want this to rotate X. Right? So if we edit the gear, you'll see that for every 1 rotation of the actual worm, we'll get 30 rotations, or excuse me, inverse of that. For every 30 rotations of the worm, we get 1 rotation of the worm gear. But the setup, the selections are identical to the one I showed you just a moment ago. So just keep in mind, worm gear, bevel gear, I'll show you in just a moment. Planetary gears, the simple gear example I gave you, just 2 gears together. All of those are using the same gear relation. There's not a separate command. It's all about defining the 2 mates that allow the rotation between them, and then setting your ratio. And again, I mentioned this, but just keep in mind, you can right-click any mate and animate it if you want to see what's going on. I can right-click and animate. Maybe speed this up a bit. But it just gives me that quick visual that, okay, this is working as I'd expect. Okay. So that's a worm gear. And again, the process of creating the gear relation is exactly the same as it was a moment ago, just selecting the 2 rotational degrees of freedom. Now, in both of these examples, I've shown you revolute mates. And revolute mates are going to be the common example because they have that rotational degree of freedom. But realize if your part is constrained using a cylindrical mate, that will work too. The only thing that's necessary is you have a rotational degree of freedom. It doesn't have to be a revolute mate. So just keep that in mind. All right, so moving on to the next type of motion that I wanted to mention here today, and that is rack pinion motion. So again, question, how would I go about creating a rack pinion type motion where I rotate something and I get linear travel in a certain direction of another part? And the key, of course, is the rack pinion relation. I've already briefly mentioned it, but we have a specific command in the toolbar for this, and it allows you to define a ratio between the rack and the pinion. So for every 1 rotation of this, I get linear travel of this part a certain amount, right? And that's what you input. The key thing here is you choose a mate connector with 1 mate connector with a rotational degree of freedom. So if you look at our arbor press example, the rotational degree of freedom is the handle, right? The handle rotates. And then 1 linear degree of freedom, right? And that's the other part in this rack pinion relation. So just keep in mind you're choosing 2 different mate connectors, 2 different, one with a rotational degree of freedom, one with a linear degree of freedom. Okay. All right, so let's get into an example of this. Now, real simple. In this case, I have a revolute mate that attaches my handle to the base, and I have a slider mate that gives me my linear travel. Right. So the key thing there is, of course, as I'm going to move it, I want to be able to say, for every one rotation of this, move this a certain amount. So I define rack pinion. I define my two mates. Right. So we'll define the slider and the revolute, then just set a ratio. Let's say 2.25. So I'm saying for every one rotation of this revolute, or this handle, I want 2.25 inches of linear travel. Right. So green check, and now grab and drag, and you get that behavior. Now, a tip, you'll notice my handle's going the wrong direction. If I edit the rack pinion, all of these relations have a reverse direction option. So just keep that in mind. If it's going the wrong way, you find that out, just reverse the direction, and you'll see it's going the correct way, right? So just keep in mind, rack pinion, if you're looking for a rack pinion-like behavior, real simple. The key thing there is a rotational degree of freedom for your revolute mate and a linear degree of freedom with, in this case, a slider mate. All right, so a few questions that I see. Bear with me. Can you have the same object rotate and move in a rack and pinion relation, such as a gear climbing a column? I would use a screw relation. And well, no, I take that back. Yes, you could. Yes, you could. I mean, the key there is that one object would have to be fixed and the other one free to move. But yes, you would use a rack pinion, at least in the scenario that you're describing. So, can you make a chain link assembly? Can you make a chain link at multiple degrees of freedom due to pivot points, but travel along a sketch path? You can't define it as traveling along a sketch path, but I will show you in a moment where if I have faces to reference, I can, for instance, like a groove cut into something, I can tell it to follow this path. And if my pieces have multiple degrees of freedom, they're free to move within that travel of the path. So bear with me. I do have an example of following a path. It's not a sketch path, but it may give you something similar to what you're looking for. So give me just a moment. The next one on my list is linear actuation. I should say, screw actuation. What if I want a threaded rod? I want to be able to twist a threaded rod and have something drive in and out. Another commonly asked question. The example I give, you'll see the vise where I twist the vise, and of course that drives it in and out depending on the rotation I twist it. That is a screw relation in Onshape. And the key there is you're defining linear travel. How much linear travel do you want per rotation of a certain mate? And so what you're doing is you're choosing either a single mate or multiple mates to define your rotation and your linear degree of freedom. And I'll show you an example of this, very simple to do. Question. So a mate is a collection of parts. Not sure I understand the term. No, the mate is how we put the parts together. The assembly is a collection of parts. So an assembly is a collection of parts. A mate is how we position those parts relative to each other. And the mate also defines how free they are to move. Question. If the ratio is wrong, can Onshape identify it tooth to tooth? The answer is no. No, you cannot identify. It's not going to recognize the two are overlapping or clashing, so to speak. So you would need to know the ratio and input that. Now, you'd be able to see it pretty obviously, but it's not going to automatically correct itself, so to speak. What about sprockets connected with a chain? We actually have a feature script feature for belts and chains and so on. I would definitely recommend checking that out. Modeling each link of the chain, I don't think is very practical in most situations. So, all right. So linear actuation, really again screw actuation, where I want to be able to drive a part in or out based on a threaded rod, for example. So let's get into this one. Bear with me for just a second. All right, so simple example of a vise. And of course, what I'd expect is as I drag the vise jaw in and out, the spindle should rotate. And if I drag the spindle around, I'd expect the jaw to move in and out. And in this case, I don't have that established. But what I want to point out is the spindle this threaded rod, is attached to the base with a cylindrical mate. A cylindrical mate allows both, rotation and moving in and out, which of course is what we need. Moving in and out closes and opens the jaw, and rotation allows it to, thread in and thread out. So this one cylindrical mate has everything that we need for our screw relation. So I select screw relation, I select the cylindrical mate from the toolbar, then I define a distance per revolution. So for every one revolution of this vise, spindle, I want a 1/2 inch of travel. Right? So green check, and now when you move in or out, you'll see the spindle moves. Right? Now I can grab either piece. So again, another commonly asked question. It does not matter, which part you grab and pull on. You can get realistic movement between them. So the key thing there is it's using the rotational degree of freedom of the spindle and the linear degree of freedom of that cylindrical mate and defining a ratio between them. Right? And that's what's giving me my realistic actuation. So that's a simple example using a screw relation to define linear actuation. The next example that I have for you is a cam, and it's another commonly asked question. How do I recreate cam-like motion in Onshape? And the simple answer is a tangent mate. In Onshape, we have a tangent mate. It's a bit different than some of the other mates in that you don't use mate connectors. You just use faces or edges or vertices, but it allows you to define a tangent relationship between parts that's maintained even through rotation, for example. So the example I often give is a camshaft, and it's, of course, pressing down valves, something like you might see in a traditional engine. But there's lots of examples. I have another example of this in just a second that's also very common. But just keep in mind, we don't have a specific cam button. We have a tangent mate, and a tangent mate is useful in this scenario as well as a number of others. Real simple, as I mentioned before, you don't use mate connectors. So this is just a matter of clicking on faces, and it will automatically recognize any tangent connected faces. Right? So let's jump into it, and what I'd like to do is show you a simple example, and then we'll get into a little bit more complicated example. And real basic, as I mentioned before, all you're really doing is clicking on the tangent mate command in the toolbar, right? And then defining the two faces that you want to bring together, right? The face of the cam, one face of the follower. It will automatically grab any faces that are tangent and connected. So in this case, you can see that it automatically grabs all of the faces of the cam, even though I only clicked one. So you don't have to worry about selecting all of them. Just click on one of the faces. It grabs everything. And then we have a tangent relationship between the two. Right? So now there's a tangent relationship between the face on this push on the follower, right, and the faces on the cam. Now, of course, the big thing here, if I animate, you'll get that realistic cam-like following behavior where it remains attached to the end of the part no matter what. Right? So that's a simple example of a tangent mate. And what I'd like to do is show you one more. And this is, of course, a little bit more detailed, but the only real difference here is that instead of just one, we have several. Right? So you'll see many different tangent mates attaching each of the valves to the cam. Right? And if we do an animate, hit play, you'll see that it rotates, and for every rotation, when that lobe of the cam hits the follower, it goes through and presses the valve. Right, so that's the idea behind the cam mate. Is it allows you to essentially just make two faces or two sets of faces tangent to each other, right? And that gives us that realistic, cam-like behavior between parts. Right? So that's one of the more common mechanisms that I get asked often about is how would I recreate a cam and a follower? And that is the tangent mate, right? So that is a tangent mate. Now, tangent mate, as I mentioned before, has a number of different use cases. It's not just for cams. And one of the commonly asked questions that I get is, how about following a path? What if I wanted a part to follow a certain groove or a certain path of some sort? And this is another example where tangent mate is useful because it allows me to define this part as inside of this part is tangent to these faces, and it will maintain tangency even when you move that part along the path. So tangent mate is another example. If you're trying to drive a part along a path, that's the mate that you're looking for. Now, as I mentioned before, you're not using mate connectors. You're using two selected faces, two selected edges or vertices, and it makes them tangent. Okay. All right, so a quick question that's popped up. Is there an interference detection available? We do not have an interference detection button, but I will say that built into our section view command, if you do a section view, you'll see anything that's interfering in bright red. So it's that ability is kind of built into the section view command. Do a section view, drag your section view through it, and anything that's overlapping will be in bright red. So following a path, again, another commonly asked question, how would I accomplish something like this using Onshape? And the simple example, I always like to start basic. I want a part to follow a path in another part, right? A groove that I've cut into another part, and I want this to follow it. And that's an example where tangent mate is perfect. And all I do is I select a face, in this case, of a part, right? And then a face of the groove, right, that I want to attach. So here, it will bring those two together into a tangent mate. And the idea behind it is now this face is tangent not just to the radius that I clicked on, but the entire groove. So as I start moving this along, you'll see it's following that path, right? So that's another example of a tangent mate, where all I'm doing is I'm putting one part inside of another and telling it to follow this particular, face or series of faces in our example. Now, this is a very basic example, of course, but this means that there's all kinds of possibilities when we talk about, how something like this might actuate other parts. And the example I like to give, and this is something that was modeled by our own Neil Cook, is this fishing reel. And the fishing reel, if you've used a standard fishing reel, when you rotate the crank, it drives that spool up and down. And, the question gets asked, well, how would I go about recreating something like that? And that's another example where I could use a path and a tangent mate, right? So let me hide a few parts. Well, let's show you the motion first. So if I grab and drag, you can see that as I rotate this or drag it up and down, it spins, right? If I were to spin the handle, it will drive the spool just like it would in real life. And the question then becomes, well, how do I get that kind of movement? And so let's hide a few parts here. I'm going to hide this external shell and show you some of the internal pieces of this fishing reel. And the thing that I want to point out, there's two things that I'd like to mention here, but the big thing that I want to mention is this part, right? Let's hide this outer gear here. Notice the path cut into this part. Right? That path, if we show our oscillating gear again and hide this part, okay, lines up with this notch in the gear. So as this is rotating, this is maintained inside of that path, and that movement up and down inside of that path is actually what gives us the up and down motion that we get from the spool. Right, so let's bring that back real quickly. And, if I were to drive one of these parts, let's say rotate it around, you'd see that the tangent mate is maintaining that relationship between the blue part and that pin in my gear. And as it spins up and down, that's what's giving me my linear actuation for it. Right. So again, it's just maintaining inside of that groove and following that consistent path, but combined with the rotation of the gear gives me that up and down movement that I expect to see from the spool. Okay. So just another example, but the key thing I want to drive home here is, think of all the scenarios you can use tangent mate. It's not specific to cams. It's not specific to paths. Anytime you need to make one face tangent with another, or maybe a combination of faces, and follow those faces, you can do that. And a tangent mate is very useful in a number of different situations. So that really is the tangent mate. I have a few different examples of it for you. I wanted to jump into our next one, which is, bear with me, the last one on my list, and that is a swivel. And this is another commonly asked question. I design suspension, or I design pneumatic cylinders and there's swivels on the ends, or there's all kinds of examples of parts where I have one swiveling relative to another. And the answer to this is a simple ball mate. We actually have a specific mate that allows you to rotate in all directions, but no linear travel, which is a perfect swivel, right? So if we think of the suspension arms that you're seeing in that animation on the left, as the suspension arms travel up and down, it needs to be free to pivot around that spindle. And then, of course, the spindle itself needs to be free to spin in order for it to steer. So that's a perfect example of a swivel. I have many others, but I'm sure you're familiar with the concept of basic swivel. Very common in things like pneumatic cylinders or suspension design, where you need to be free to rotate in all directions, but no linear movement. So I do have a simple example of this swivel, and it's a front suspension. And as I mentioned before, the key thing with a suspension like this, it needs to be free to pivot as the control arms move up and down. Right? So as I drag this up and down and the shock compresses, it needs to be free to pivot, but also it needs to be free to rotate. Right? So as I grab and drag, it needs to be free to spin as well for our steering. And the key thing here is all we're doing is defining a ball mate between the swivel and the eye. Right? So swivel eye, define the two center points of the swivel and the eye, and then give it a ball mate. As mentioned before, it allows it to rotate in any direction, but doesn't allow it to move in X, Y, or Z. Right? So that is a ball mate, and again, very common in the example of a swivel. And another frequently asked question, how would I create swivel-like behavior, swivel-like motion? So that is what I had planned for you. I'm going to stick around and answer any questions, so feel free to ask any questions that you'd like. Again, there's a questions dialog in your GoToWebinar control panel. Feel free to ask any question, and I'll do my best to answer them. I will stick around and answer any questions that are there, so again, feel free. I do have one final question for the audience, so bear with me. Are you interested in a private demo or discussion from an Onshape account manager? More specific maybe to your application, to your design, to how Onshape might fit into your business model. So if you're interested in a private demo or discussion with one of our account managers, definitely let us know. You can hit yes, and we'll have one reach out to you. Again, I'm going to stick around and answer any questions that you have, so feel free to ask any questions in the questions dialog. But that's it, everyone. Thank you, and have a good day.